So we move on to the SciPy.Signal module, still looking at the SciPy library. Don't forget SciPy is scientific Python, and it's very useful in scientific computing for doing, you know, for doing a lot of tasks. So in the last video, we had considered the SciPy.FFT model, which talks about transforming signals in the time domain into frequency domain. And while using FFT, we stumbled on the need to use SciPy.Signal at some point because it's all about signals, right? So the SciPy.FFT and SciPy.Signal, they have a few things in common. So SciPy.Signal is a powerful module in SciPy used for signal processing tasks such as signal generation, filtering, spectral analysis. By the way, I have a spectral analysis playlist already. You want to check that out if you want to know the nitty-gritty of these things. Then convolution, correlation, Fourier transforms, system analysis, filter design, and it is widely used in audio processing, biomedical engineering, communication systems, radar and sonar, control systems, of course, scientific computing in general. So we talk about signals and sampling for starters. A signal is a varying quantity that carries information. Okay. So, and it can actually come in the form of a data set or in the form of a sound document or an audio document, a video document, and things like that. So, examples include audio waveforms, ECG signals, sensor readings, and radio transmissions. So um, the sampling frequency is given we saw that in the last video too. The sampling frequency is given as Fs, which is 1 over T of S, T sub S, where F sub S is the sampling frequency and T sub S is the sampling interval. Okay, so the Nyquist criterion to avoid aliasing is Fs greater than 2 times the maximum frequency, like that. So we saw that also in the last video. So here now, if you to create the time axis, if you have fs to be 1000 and t is 1, then so the time axis is from 0 to t. That's from 0 to 1 in 1000 divisions, which is fs here, right? So if you want to print the time now from the beginning to up to a step short of 10 or so, so you have 0, 0 0.001, 0.002, all the way to 0.009. So you're printing that. So that's the time axis, like that. Then you then want to, if you want to generate a sine wave, so you have a sine wave which is defined as x of t rather equals sine 2 pi ft. So this is actually the signal in this case now. So it's coming in form of a formula or even a data set. So where f is now the frequency and t is time. So to generate that sine wave, you use this simple code right here. So here now f is 5. If you take the frequency to be 5 hertz and the sample is 2 pi ft, what we saw up there. So now our f, the frequency is 5. So and then you just plot t comma x. So you plot the signal against time, and then you have time on the x-axis and amplitude on the y-axis for the sine wave. So and this is exactly what you get. So you have the time running here from 0 to 1, and you have the amplitude on this other side, like that. So for the cosine wave, you have a cosine wave, which is also a kind of signal, is x of t equals cos 2 pi ft. So if you take the same f like we did before, so all you just need to do is define this now as np dot cos. np because the cos function can only come from NumPy library. Same for pi function coming from the NumPy library. Then f we defined before to be 5, and then um, you then have all of that. So if you run this now, of course, you know the major difference between sine wave and cosine wave is that the sine wave starts from the origin, while the cosine wave doesn't start from the origin. Did I run this initially? Okay, I did not. So it's probably going to affect the cosine wave. Okay, let me stop this. Yeah. So let me stop this. So run this first. Okay, I didn't start by running from this. So okay, this. Yeah, then this follows. So sequence, because each one depends on the previous one. So the sine wave starts from the origin, while the cosine wave doesn't start from the origin. So, it's starting from 1, while the cosine sine wave started from 0. Okay, so you can have square waves. So SciPy can generate square waves using signal.square. So if you need a square wave, so a square wave is now signal.square of 2 pi 5t, you know. So instead of having the normal sine or cosine, you can have it in square form, but it's the same signal. So just take the square. So, and this is what this looks like now. So it's actually still fluctuating like a cosine or sine wave, but then, it's like in the square form like this. Then you can have sawtooth waves. So it's the same signal can be represented as a sine signal, as a sine wave, cosine wave, square wave, or a sawtooth wave like what we have here. Sawtooth waves are periodic non-sinusoidal waves. So what you need to do for that is saw wave is now like signal or sawtooth, then of the same signal, 2 pi ft, 2 pi 5t. So if you run that, you get this kind of, so like the edge of a saw, like that. So it is non-sinusoidal, right? But it is periodic, so it keeps going up and down like that. So this goes, comes down, goes, and it follows the same pattern. Then you have convolution. Convolution combines two signals. Mathematically, y of n is equal to x sub n convoluted with h sub n rather. Convolution is fundamental in filtering, system analysis, and of course, image processing. So it's more like you're fusing two ideas together, two images together or something, two signals together. So if you have H to be 1, 2, 3, and sorry, X to be 1, 2, 3, and H is 0, 1, 0.5. So Y signal dot convolve. So you convolve the two, that's X comma H. So you print the Y, which is the result of the convolution. Then you have 0, 1, 2.5, 4, 1.5. So it just does its own thing and gives us these outputs. That's what the convolution does. So we also have correlation. Correlation measures similarity between signals. So you have correlation of signal. Correlation is signal that correlates x comma h. The same two waves now. The same two signals, we want to correlate them. So if you to print the correlation, you then have 0.52, 3.53, and 0. So correlation measures similarity between signals. How similar are these signals? Then we have Fourier transform. So the Fourier transform converts a signal from the time domain into the frequency domain, just like we saw in the last video. So the discrete Fourier transform then is x of k equals summation from n equals 0 to n minus 1, x of n e raised to minus j 2 pi k n all over n. Then you have the FFT example, just like what we brought from the other case, fast Fourier transform. So we did things like this a lot. So here now you're putting two signals together. That's a signal of 50 hertz and another signal of 120 hertz joined together in this Fourier transform. So like this summation you have right here. So by the time we do all of that, we have this, and then of course from the equation, you already see 50 and 120, and that's why you see those sharp amplitudes at 50 and 120. So now this is easy to identify already because from the formula we can already see it. But if you're working with a data set, so until you do this, until you run this, you may not be able to identify those sharp signals like that. So we talk about digital filters. Filters remove unwanted frequencies. So types of filters include low pass, which removes high frequencies, high pass, which removes low frequencies, and band pass, which keeps selected frequencies, and band stop, which remove selected frequencies. So depending on what exactly you want to achieve, you can have a low pass, high pass, band pass, or band stop filter. Okay. So we have FIR filters, finite impulse response filters. Those are FIR filters, and they're always stable and they can have linear phase and are easier to analyze. So a filter is an FIR filter design. So if you have num taps 50 to be 51 and the cutoff is 100, the frequency sample is 1000, and B signal FIR win num taps. So you have the 51 cutoff 100, FS is FS, and then you print, you get something like what you have here. So this is almost like zero. This is 6.2 times 30 to the minus 19. This is as good as zero. This is not so close to zero like that. Okay. So you have the FIR filter design. So the actual filtering then happens in which you can visualize. So the filtered now will now be the signal dot L filter of the B you have up there, then 1.0x. Then you can then plot the filtered signal right here. So you have the filter signal this way. So it still looks periodic like sine and cos, except that it's not sinusoidal. So IR filters, apart from FIR filters, we have IIR filters, which are infinite impulse response filters. They use feedback, they are computationally efficient, and they can become unstable. So for instance, we can have a Butterworth filter where you have B, comma A to be signal.butter 4, 100, B type low, FS is 1000. So this B type here, I want to suspect that it is the low pass filter, removing high signals, high frequencies. So then you print B and you print A. So B, you have all these values now, and you print A, which gives all these other values you have right here. So if you apply IIR filter now, so that's signal.L filter B, comma AX, and you plot that, and you have the IIR filtered signal. I think I've missed a stage. Okay, this has been run. Then this is the next one. Yeah, before we come to apply the IIR filter, which is okay now. So you now have the IIR filter this way. Okay, then you have zero phase filtering. So fields performs forward and backward filtering. Advantages: it removes phase distortion and preserves waveform shape. So, all this filtering we are talking about, right? Imagine you have a sound and there's a lot of noise in this sound. So this is actually what happens when you work on that kind of sound and you remove all the noise. So, so the fields performs forward and backward filtering, and the advantages include removing phase distortion and preserving waveform shape. So here, imagine Fs is 1000. That's sampling frequency. T is from 0 to 1 in 1000 steps, 1000 divisions. Then the clean signal is sine 2 pi 5t, and the noise is 0 0.5. So noise is randomness, right? The noisy signal is now the clean signal plus the noisy signal. Then you now apply the BA signal butter 5, 10, and then the filtered signal will now be signal.filters or BA for this noisy signal. And then you do your plotting, which takes us to have this. So you have the noisy one. As you can see, it's really chaotic, but the filtered signal looks really clean, and the noise has been all removed. Then we have talking about spectral analysis. I have a playlist on spectral analysis, like I keep saying. So spectral analysis studies frequency content. So important methods in spectral analysis include Welsh, PSD, periodogram, and spectrogram, which I explained in some depth under the playlist on spectral analysis. So you want to check that out. So just go to my channel and click on playlists. Then you find spectral analysis. So the Welsh power spectrum, you have F, PXX, all of that, and semiology, FPXS, and then you do your plotting and you get something like this. So you have the frequency on the x-axis and the PSD, the power spectral density on the y-axis, and you see the shape following that, like looking like some kind of M or W if you like. So spectrogram now. So the so, we are just touching on the important methods in spectral analysis like Welsh PSD, periodogram, and spectrogram. So if you want to learn more, check the playlist, like I said. So here now you have F, T spec, SXS for spectrogram now. So you have signal to spectrogram, X, FS. So it's the same X we've been dealing with before we came here. Then you then plot the P color mesh, T spec, FXSS. So the Y label is frequency and the X label is time, and the title is spectrogram. So you plot this, and this is what you get. So you have all of this. So you have something happening around 50 hertz frequency and something happening around 120 hertz frequency. So remember the original plot, that was the original signal, was a combination of two signals, one with 150 hertz signal and a 120 hertz signal. That's what is being carried out here for the spectrogram. Then we have window functions, which we also talked about under the fast Fourier transform playlist, fast Fourier transform video. That's the last video now for SciPy.FFT. So window functions now. Windowing reduces spectral leakage. So common windows include Hamming, Hahn, Blackman, and Kaiser. So in the other case, I think we used Han or so. So here we are using ham. I mean, they actually look a bit alike, except that each of them has some specific areas where they are good. So for the window now, if you now have signal.windows.hamming. So it's the same signal we've been using before now. Same signal we've used in previous places. That was the same signal we used here. The first place the signal was declared. So we also use that signal here. So I want to trace it back to where the signal was first called. So here we have the signal, the noisy signal still here. Okay, I think that was referring to the original signal. So I want to see the original signal, the very first place where the signal was used. Um, where is it now? Signal. Yeah, I think it's somewhere here. Signal. The first time ever, the signal. Yeah. Okay, I think it's the same signal that was defined. That signal signed by 5T or so with or the one that was combined later. So yeah, we have for the Hamming now. So Hamming window. So we have window signal.windows.hamming 128. So you have to specify powers of two. Then plot window, and then you use the Hamming window. So and this is what you get like that. Then you can also resample. Resampling changes the number of samples in a signal. So in data analysis generally, right? So sometimes you have some data that that are not so suitable for the purpose you want to use them for. So there are some standard procedures for changing maybe a daily data to weekly data to monthly. So depending on the actual need you have, so you can always resample data like that. So a very good example is X resampled can be signaled or resample X by 500, and then you print the length of X, which is now 1000, and the length of the resampled is 500. So it's more like you have changed the length of the sample from 1000 to 500, depending on your need. Then there's also the idea of peak detection, which we also saw in the last video. Peak detection is used in ECG analysis, radar systems, event detection, and spectral analysis. So for peak detection, we used a bit of that in the last video. So for peak detection, imagine you have X is sine 2 pi 5t, then x plus equals 0.2. So you have some noise being added to that. So you have peaks and properties of signal.find peaks. So you want to look for peaks now at height of 0.8 or something. So plt.plot t comma x. So by the time you run this, you then find some peaks, right, on each signal like that. So then you can identify the highest peaks on each high part like that. Then we have transfer functions. A transfer function model system behavior, like you have h of s equals 1 over s plus 1. So transfer function signal is signal dot transfer function 1 comma 1 comma 1. So if you print the system, you then have something like this: transfer function continuous array 1 comma 1.11. So you have all that. Then you can also talk about step response. The step response shows system output for a unit step input. So we have t step, y step equals signal dot step of whatever system. I think we came up, yeah, the system is coming from here now. So if you plot that, this is the kind of thing you get. So you have the step response this way. So it reaches some kind of saturation. Then you have both plots. Both plots visualize frequency response. They include magnitude response and phase response. So phase response is the angular response, like that. So for both plots, you have W mag phase signal dot both system. Then you plot the PLT figure, semilog X, and all that. You have the magnitude response and phase response in two different plots. So for the magnitude response, you know, from 10 raised to minus 2, that's 0.00, yeah. So up to 10 raised power 1, which is 10. So this is the kind of decline you have. And for the phase response, you have so it starts and then it eases out that way. So not as sharp as the magnitude response. Then you have chirp signals. So a chirp changes frequency over time. Okay, so if you have t to be from 0 to 10 in 5,000 steps, 5,000 divisions, so, and you have x to be the signal dot chirp. So you have t, you have frequency 0, that's 10, frequency 100, time 1 is 10, and the method is linear. Then you plot t against x for the linear chirp now. So you have this, so you can see how this one comes. So you see that it's changing frequency over time. Then you have the Hilbert transform, which creates an analytical signal. So Hilbert transform example, analytic signal dot Hilbert of x. The envelope you have np dot absolute value of analytic, and then you plot c against x. So you can develop an envelope as we have in this particular one. I don't remember. Did I? Okay, I did run that. Then here, for the Hilbert transform, you also run this. So we then have the Savitsky-Golay filtering. Savitsky-Golay filtering smooths noisy data while preserving shape. Okay, so from SciPy.Signal, we want to import filter. That's the Savitsky-Golay example. So the signal is sine 2 pi 5t. The frequency is clearly 5. So the noise is 0.3 times some random stuff. And it has to be of the same length with T, right? So it can fit together. X noise is now X plus noise. So to smoothen that out, you have the Savgo filter of the noisy signal, 51 by 3. Then you plot as usual. So if you want to know more about this, you can actually, check. You can copy the code to AI and then every line is explained to you. So here we have you have the noisy data in blue and then the filtered data is in orange as usual. Um, then we have performance tips, right? So you need to use FFT-based convolution for large signals. So that's signal.fft convolve. Then use second order sections. So improve second order sections improves numerical stability. So you have signal.sos fields, and then you have common pitfalls like aliasing, which occurs when the sample rate is too low. So that's about the sampling. Normally the sampling frequency should be at greater than twice the maximum frequency. So for it to avoid aliasing, so you want to make sure there's no aliasing by making sure the sampling rate is not too low. That is for obeys that criteria, that the sampling frequency should be greater than twice the maximum frequency. Then for edge detection, filtering may distort signal edges, and improper normalization. Some functions require normalized frequencies. In summary, we see that the SciPy.Signal module provides tools for signal generation, FFT analysis, filtering, spectral estimation, system analysis, transfer functions, peak detection, and resampling. It is one of the most important scientific computing libraries in Python. So basically, if you are into signal analysis and things like that, you want to use SciPy.Signal and of course SciPy.FFT because they seem to overlap in some ways. So you want to use this to if you are into spectral analysis or some kind of signal processing, be it sound, audio, video, whatever it is. So we have some practice problems here for you to try your hands on. So they'll basically require you to just look at the codes that I showed you in the lesson and then just adapt them to whatever you have been told to do. So you have questions 1 to 7. It generates a 5 hertz sine wave sampled at 1000 hertz for 2 seconds. Generates a cosine wave. You have all of that going. The last question here is generate two sine waves of different frequencies and combine them. So there's an example of that also there. So intermediate level, you can design a low pass filter, FIR filter using signal.FIR win. Then last resample a signal from 1000 samples to 250 samples using signal.resample. So we saw how a 1000 sample signal was converted into was resampled into a 500 sample signal. Then we have advanced level like this. So you want to detect peaks in an ECG-like signal using signal.find peaks. So you want to identify the peaks in those signals. Then you create a chirp signal whose frequency increases from 10 Hz to 200 Hz over 5 seconds. And you can build a transfer function using h of s equals 1 over s squared plus 2s plus 1 and plot step response. Then create a complete signal processing pipeline by generating a noisy signal, filter the signal, compute the fast Fourier transform, detect the peaks, and visualize all the stages. And with this, we come to the end of this interesting video on the SciPy.Signal module, which helps deal with signals. And like I keep saying, the signals do not have to be formulas necessarily. They could actually be data sets. So that's what we have there. Let me know how helpful this is for you. And if there's something that you'd like me to try out, feel very free to let me know. If you have subscribed to this channel already, I thank you very much for doing that. And if you have not, why not go ahead and subscribe right away and hit the notification bell so you can always get alerted each time a new video is released. So having done that, you can also become a member of the channel by clicking on join. That gives you special privileges like getting to see some videos before others see them, or seeing some videos exclusively as a member of the channel. You could also request for PDF copies of some of the notes I use. By the way, these code sheets are available on Google Drive. Just look at the description box of your on WhatsApp or on YouTube. You'll find the link to the Google Drive where you can download this code sheet. What I always advise is you download the sheet first before you start following the video. So if you have not done that before you get here, maybe you want to do that again. So you can maybe you can now use the code sheet to try out some of the the practice problems. Okay. Ultimately, don't forget to comment, like, share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.